Alrighty. Hello everyone and welcome to Handmade Hero, the show where we code a complete game live on stream. We have some work to do today because we wanted to finish our bounds checker. We basically implemented our own memory bounds checker that allows us to know if we ever overwrite blocks of memory that we've allocated. But we haven't quite finished it. We sort of got the basic version working yesterday, but in order to finish it up, we kind of have a couple more things we need to do. And so that's what I'd like to do today. And basically, there's two things we need to do. One is we need to manage our headers a little bit better, and the other that we need to do is implement something that shifts memory up towards the end of blocks so that we can do overflow testing as well as underflow testing. Right now, we're only doing underflow testing. So let's go ahead and get started, since there's really not much to explain. It's all the same concepts as yesterday, but we're just finishing up. So today is day 346. You'll want to do day 345 source code if you're going to be following along with me. So let's go ahead and build and run the program. There we go. So all we're doing right now is we're doing the, like I said, we're doing the underflow testing. Let's go over here. Platform allocate, or try to platform allocate. So all we're doing right now is we're doing underflow checking. And we did something interesting here. In fact, I never really did this before. I'm not sure why I never did this before. And I'm thinking that I probably will. I might change the way I do things now that I've done it this way here on Handmade Hero. I never really, I just never really thought about it too much. And probably I should have. Let me open up Milton and just briefly say what I did yesterday in case, for those of you who missed it, it was just kind of weird. Let's see, day 346, day 346. My tablet seems to have is no longer treated as a tablet, perhaps by Milton or anybody else, by the way. I'm not sure why that started happening. It happened after I did that thing with the I accidentally let the program run and use up all available memory. I don't know if you guys remember that. So I'm not sure if I should try to get the Wacom drivers to go back into some state that makes some sense. Probably I should do that after the stream, but we'll try it really quickly now just to see whether that helps. It doesn't help. Yeah, Wacom driver, how are you doing? The tablet driver was not found. So, you know, not great. No tablet driver, and so Milton is, Milton can't really access the tablet if there's no tablet driver, to say the least, so I guess I'll have to reboot the machine at some point. Anyway, ladies and gentlemen, the robustness of Windows. Day 346. Let's just go ahead and mention here what was happening. So what I did was I needed to make a page of memory for the allocation. And we don't really know how many pages that is. That could be any number of pages, right? So this is like n pages here, because if the allocation is, 36K, then we need at least, to fit the 36K, we would need, well, I probably should have picked something a little bit less convenient as, oh, well, no, that's fine. I take it back. Let's do 34K. So we know that we need things in 4K page clumps because the operating system only manages pages in 4K clumps. So if I was to divide 34K by 4, I would get 8, and then I would have a remainder of 2K, right? So I know I have 8 full pages, but then I'm going to essentially need 9 pages. I don't know why I put that there. So I need 8 4K pages to fit the 32K, and then I would have 2K left over. And so what I need is I need 9 pages total. One of them will only have 2K in it. It won't have the full 4K, right? So I need essentially 9 pages for, let's say, that allocation. So in this case, n would equal 9. And then what I need to do is I needed to basically put guards on either side of it. And I should stop saying guard page because it's not really what I mean, but dead pages, fault pages. I need to put one page, so this is a 4K page, this is a 4K page, right? that are marked as like, do not write to these, so that we can get checking on either side. We can only get perfect checking on one side or the other because, again, if the allocation turns out to be not rounded to a 4K boundary, then we're going to have some blank space somewhere. And we can either put the blank space at the beginning and have it end right at the upper end, or we can put the blank space at the end and have it end right at the lower end. But we can only fundamentally check for underflow and overflow perfectly in one direction at a time, right? We can only do one of those at a time. So if we're doing this, it also points out the fact that it's unclear where we put the memory header. We can stuff the memory header into this unused location if it happens to be big enough. But what I did, which is kind of fun, is I made one other 4K page that's just for the memory header over here, right? So there's a page beyond the page that's there for overflow detection that's just for that purpose. And that seemed kind of interesting, and I liked that. That was kind of a cool, I don't know, I thought that was kind of interesting. So what I might do is just double down on that. I think that's kind of neat, so I think I might just go with that and make it so that that's actually how this works in general. And what I mean by that is currently what we're doing, if we kind of go into our memory system here, currently what we're doing is when we allocate memory, we put the size of that block, we put that into this to the chain, right? I'm sorry, we put that into the allocation, the size of the memory block chain. We're doing that outside in the platform independent layer, right? When we're saying, hey, let's go ahead and have the memory allocator here that's actually doing reading allocations. Every time it needs to get a new block from the system, it's adding space for like a little chain thing of its own. But what I'm thinking is, I wonder if it wouldn't make more sense to actually have it so that the operating system allows us to get, or we like share that thing with the operating system, if that makes sense. And there's two ways we can do it. One way is we can have the operating system put it in a special location like it was doing before. The other way we can do it is having it be part of the block that this thing manages. And I don't know which one of those is the best way to do it. What I do know is that we could essentially change the API to the system, and I kind of like the idea of doing that. I kind of like the idea of changing the API to the system so that people who allocate memory from the system actually understand the fact that you're getting back a thing that has a control block in it, right? And that you use that control block for storing your information as well, if that makes sense. And so what I mean by that is if we look at the platform layer, and again, I'm just kind of experimenting with this, but because I just like the idea. When we say that we want to do a platform allocate memory, right now we're just getting back a void star, which is like a pointer to the memory. And when we free it, we pass in a void star, and we also pass in whatever the flags were. And again, the reason that we had to pass in what the flags were is because fundamentally speaking, the operating system doesn't have any idea how the memory was allocated in the first place. So in order to get back to its control block, it needs to do work. So what I was thinking is, really, we don't have to do that if we don't want to. We don't necessarily have to even deal with that particular situation, because what we could do instead is actually have the platform memory header or actually have the Win32 memory header be like a real thing that you get back and that you can see, right? So if you imagine, we take a look here, we've got this sort of Win32 memory block thing. And just what I'm thinking is, we could make you basically get back, a pointer into a part of this or into actually this, right? So for example, we could say like, okay, what is the portion of this that should be visible to the application? And if we take a look at it, it's like, well, it's probably, something like this, right? These things are pretty much stuff that only the Win32 side cares about, but these things are things that the application would potentially care about as well, right? The flags are something the application was having to pass back into us that it could keep. The size is something the application wants to know about the memory that it allocated, right? Because it's trying to track that as well. The base pointer is the thing that it primarily wanted in the first place, was where the memory is. And then we've got two more things here that are, sized appropriately to actually have them come back to us as necessary. And so what I'm thinking about that, again, is just that, hey, it would be cool if we could make it so that this was effectively some struct platform memory block where we just said all of these things are actually in here. Or maybe that. I don't know. Something like this. I have no idea what it should be. Game block, maybe. So anyway, inside there, I have no idea. Subblock, block, I don't know. Anyway, point being, the memory block sort of exists inside there, and so when we allocate one of these, we could pass the the person who's calling us back one of these things. So for example, we could then make the allocate memory and deallocate memory stuff actually work on one of these platform memory blocks. And return one of these platform memory blocks. And so then what we could do, and also that would alleviate the need for us to deal with that, then what we could do is sort of see how that would work out in our scheme. So when we want to do like deallocate memory and we're trying to free something, right, we would pass it in the memory block that we actually cared about, right, the block header. So when we say get footer or whatever, what we need to do here is figure out, for arenas and stuff like this, we need to figure out where these blocks exist, right? And in order to do that, I think what we could do, I don't think it'll be particularly difficult. I don't know yet, though. What we could do is say, all right, so the blockchain is gone. We'll just say that the blockchain is something that, again, is now lofted up into here, because it already has most of the data, right? We know where the base pointer is. Here is the base pointer. We know what the size is, because there's the size. We don't know what the used is, and we don't care about the pad. So really all we're talking about is this, right? Because those things were almost entirely storing the same information, which is why I kind of wanted to collapse them down. It just didn't make any sense to have both, right? So once we have that platform memory block, then that means that all we have to really do, like we've got get footer here on the arena, the memory arena where it's got this base pointer, what I want to do, I think, is in addition to the base pointer, I want to store what the block is, what the platform memory block is. That's the pointer to the previous platform memory block, right? And we can chain these backwards because we only ever go backwards through them. So we also should be able to say, like, OK, platform memory block arena prev or something like that, right? So we should be able to chain them backwards. That way, inside a given memory arena, we can just say, like, OK, there should be a memory block that is the memory block that we actually are using currently. And we just remember what that is, right? We just remember whatever we wanted that to be. And so that would be, something like that, right? Now, there's a bunch of stuff that's kind of doubly stored here. And the question is just, I don't know if we want to double chase the pointers or to keep them copied out like we kind of were before. Because if you take a look at what happens here, we obviously have, and I'm going to make that a U8 for now. We obviously have base stored in both places. We have used stored in both places. We have size stored in both places. So we don't actually need that data. We could just always use it off of the current block itself. But it does require us to say, well, if we have a memory arena, instead of looking directly into the memory arena, we're kind of looking into some side buffer, to every time we want to do an allocation. And I don't know how I feel about that. So I'm going to do it that way because I think it will be easier to make things work properly at first. But it may be the case to do, Casey, if we see perf problems here, maybe move used base out to avoid that sort of double indirection that's going to happen, right? So I don't know, memory allocation is not something that happens that often inside Handmade Hero, so it's possible that it isn't really relevant, but you never know. So I'm just going to like sort of mention that there is potentially a problem there, and we'll see what happens when we get to it. So okay, that would be sort of the new way that things would look. And then, when we sort of need to do stuff here, what we can do is say, okay, where's our push size? Inside our push size, when we do our sort of used plus size greater than size stuff, obviously this would require that we have a current block, right? So if we have a current block, and then we're just going to say, all right, the current block used current block size, right? And do you see what I mean about the double indirection? So you can kind of see how that's, it's not great, right? It's not necessarily what we would want to do there, and it really just depends on the circumstances whether that would be problematic or not. So anyway, let's take a quick look at the other way that this stuff would work. You can see here, like these guys would also need to have it. So yeah, you can just see why I'm like a little bit nervous about why having that constantly be the case. I also don't know when we do get effective size for. That's one of the problems that we have had and still have at this point. Is get effective size for is not going to take into account the fact that we may allocate a new block of memory at some point. So get effective size for is only useful in the case where we know that our base pointer is actually, that we know that we're not doing our like overflow checking and so on. So that's a little bit squirrely as well because, yeah, I don't know. I guess it doesn't really matter because we sort of rectify that later on, but still it's just a little bit weird. Anyway, so when we call get effective size, we also have this problem. But again, we can sort of make that be a thing where if there wasn't a current block, this should be if not current block. If there wasn't a current block, then we wouldn't do it. So we could also do a thing that was more like, if arena current block, do it, otherwise don't, and so on. So anyway, if we know that we don't have a current block, then we know we're going to have to do that. If we do have a current block, then we just need to see if it has memory. Once we get in here, then we're going to go ahead and do everything pretty much the same way we used to do it. Let's go current block here, current block. And then I think we're all good. Like so. And again, I'm going to want to revisit this a bit just until I get it down to like a place where I'm happy about it. But anyway, so that's the basic idea there. And what we're going to need is when we actually do this sort of allocation, you can kind of see we do a memory blockchain save here. That would now go away because we wouldn't be dealing with that anymore. And so then what we would do is say, all right, we know that we don't need to do this anymore. So really the only thing we're doing is making sure we never allocate a block size that's too small. We then go ahead and say, let's take, we don't care about any of this. No. That's going to get filled out for us by the platform layer. So now our current block, or I should probably say arena current block is new block, that we're now going to have a platform memory block where we do a platform allocate memory, and we tell it the block size and the flags that we want to use for allocation. That's going to get us back a new block that's going to be completely initialized, and yeah, that's about all there is to it. We no longer need the block count because the block count was strictly there to prevent us from unwinding too far. In this case, we now know that we won't have to worry about that, I don't think. because we will have the back pointer in our heading, so we will know when we've rewound too far. So once we get a new block, we need to set the arena prev. What do we call that? Arena prev. We need to set the arena prev to be the block that we're currently on. And then we set the new block to be the one that we're currently looking at, right? And that's pretty much all there would be to it. We don't need the footer stuff anymore. We don't need any of that because we're assuming that we're just going to use the one that the operating system laid out for us. And so I think the rest of it kind of is the same as it would be. Again, this stuff here has to now have sort of a block-based thing here. And yeah, all of this is how it is. I don't know who is still calling get arena size remaining. Only the person who prints this thing out. So I think that's not going to be a thing we do anymore, would be my assumption. So I think we're just going to say, let's nuke this. And then in our memory system here, we can just say that's not a thing anymore. All right. So let's see. Arena has room for. And that is also not being used anymore. Go, nor is get footer. So we can just simplify that stuff down a bit. All right. When we do the begin temporary memory, I believe that there isn't anything in particular that's going to be happening there that that needs to be special. I think it should be pretty basic. Yeah. So I think when we do begin temporary, that's all we would need. When we come back here to, you know, I'll be honest. Yeah, okay. So the when we were doing the block count thing, we were just doing that so we could clear memory. So again, yeah, we definitely don't need that because all we have to do is just keep walking back. So all we have to do is say, as long as there is we just have to say while there is a current block, all we have to do is just do free last block, right? That's really it. And so that way, when we do free last block, we just say like, okay, the thing that we're gonna free platform memory block is the current block. We're then gonna deallocate that memory, right? Whatever it is, we don't need the flags anymore, and that's really all there is to it. Before we do that, before we free it, we need to get the arena, the prev out of it, so we can move back one block. But that's about it, and that's all we should really have to do, I think. I mean, I think that's really it. So yeah, we could also make this a little simpler and say the base part here could actually just be a block. It's like what block you were on instead of what base you were on. So we just need like the block. We could do like that. And then that way we can say, well, the current block is not equal to the block that we were on before. I think that's really all there is. So that way the temp mem would not be storing a base pointer. It'd just be storing a platform memory block. Right, and I think that's it. Did I type it in wrong? Yeah, I did. Block. There we go. So yeah, I think that's good. What else we got here? So subarenas. I don't know that we're using subarenas anymore. Let's double check. Because I don't think that we are, so let's just get rid of those. All right. And when we do draw arena occupancy, that is not even something that we're doing anymore. But I think at some point we will want to enable it, so I'm going to leave that there. All right, so now let's get down to the Win32 part of things, right? So now what we need to do is take a look at how I specified this on the platform side. We moved those flags into the platform part of it, that part of the flags anyway. So we just need to take a look at anyone who was using that. The base pointer was also in there, but I don't really remember how we were writing this out. Yes, that is how we write it. So we always want to access the platform block for these, because these were all things that were in there. And let's take a look here. So allocate, we're going to want to rewrite now, and deallocate as well. Let's just make sure. OK. So let's go ahead and rewrite these now that we know what's going on. So in this case, we're going to take a Win32 memory block that we have allocated in addition to, and we're going to set up the values in it. You can see here we're setting up some of those values, like we're setting up block base, right? But we're not setting up some of the other values, like block used and so on. Those, I guess, can be cleared to 0, I suppose. So maybe it doesn't really matter that much. They all should be set to 0. But let's assert that they are. So when we set the block, let's just assert. Let me go ahead and set these here. Equals. Cannot convert from Win3 memory block to U8. Sorry about that. Here we go. And there we go. So now all I really want to know now is what exactly, excuse me, what exactly those other values are. Virtual alloc should set them to 0, but I want to make sure. So these two should both be set to 0. So I want to do an assert that my block values here are always initialized. I believe they should be, but I just want to ensure that they are, because maybe they aren't. When I return the value here, I actually am not returning the Win32 block. I'm returning that sub-portion of it, right? Because I'm not actually telling the platform layer about the Win32 side of things, so I'm just kind of returning it a little baby piece. And then that should, in theory, be all we need to do for the allocation. When we deallocate now, we know that it's actually passing us in a block, right? So if we take a look at the deallocation call, which should be here, we should be getting now a block pointer back instead of memory, right? So now all we need to do is say, well, OK, we know that what they gave us was like a plat block, was the platform part of the block. So I need to back up now to get to the correct part, to get to the Win32 part of it, right? And if I want to, I can make this a little easier on myself by just using sort of the standard subclassing way that things work in C and C++, which is that if you have a pointer to something, if you put something at the top of it, you can treat that pointer interchangeably, right? This is how C++ implements their sort of light polymorphism that they have when you do inheritance or stuff like that. You could just say, oh, all right, well, I have a memory block. I want to sometimes treat it as just a regular block. So I don't want to have to do the pointer math to move. Like I could, right? If I left it down there, when I want to go back to a Win32, I just have to know I have to move back by a few pointers, right? By 3 64-bit values. But what I can do instead is just use it this way, and then casting just works. You don't have to do any arithmetic. So since there's no reason for me not to do that, I suppose I might as well just do it that way. It's a little more efficient. So I can just say, like, OK. Like so. Now, in this case, I don't have to do this check anymore because I know that I'm actually getting back the actual block itself. So really all I have to do is use this to check the looping flags and see whether I needed to do anything. Otherwise, I'm pretty much done, right? I can just free the block as I normally would free the block. That's really all there is to it. So I think there really isn't very much to do there. Oops. That's really all there is. And I think that's it. OK. So let's see. That's supposed to be an or, not an and. So that's not going to go well, to say the least. You can't just, or an and. Not interchangeable. So if we have the current block and we're saying that it's not set to anything, that means we automatically have to take this path and allocate some new memory for ourselves, right? But otherwise, then we want to check to see whether the current block has, room or not. All right. That does not look good at all. What's going on here? Well, in this case, I can just step in. So I'm gonna. Here we go. So let's see. We have a current block. Oh, wow. That's great. I don't know what's going on there. Obviously, when I get the size, I had to set it to this. When I cut and pasted, that was a little bit of a bug there. I meant to still set the size equal to that. That was just a total typo. OK. All right. So now let's see what's going on here. We're doing a begin temporary memory. And I guess we aren't properly handling the case where we don't have a current block, where the arena hasn't been used at all. Because we're looking at that used pointer, which is not correct, right? So I suppose what I should do there is make sure that we handle that correctly. I don't think there's anything I can do. I probably just have to check to see if there is one or not. And then when we do the rewinding, in theory, that will just work. But we also, again, we can't do these assertions here. So what we would have to do is say if arena current block, if we rewound all the way, we don't want to touch anything, right? All right. So now, in theory, we're running OK. And we're running entirely in underflow checking mode right now, I believe, because we kind of did a little thing in here where we, I'm sorry, overflow checking mode, where we stuck a little thing in here. But at the moment, although we will do this part properly, meaning we'll force allocations to all be every time you call it, it'll do a separate virtual alloc and create the pages. We don't actually support overflow checking in here. So for example, we've got underflow checking support here, but we don't have any overflow checking support. So we want something where we're going to do like platform memory overflow check, right? And this gets a little bit tricky. Because now we can't just do the basic thing that we were doing before, where we sort of allocated the memory and then pushed the pointer forward a few pages. That's not going to work because now we need to make sure we line it up at the end of a page, not at the beginning of a page. Now, I believe we should still be able to say, yeah, I think, as long as we allocate those 2 extra pages, I think we'll probably be fine because the allocation that we get back, I mean, let's put it this way. I'm going to do the math out properly, even though I think we may be able to cheese it just because we know the operating system is going to allocate on the 4K page boundary anyway, but we'll ignore that for a moment. OK. So if I have this underflow check on, I know I need to add 2 pages. If I have the overflow check on, obviously I still need 2 more pages. One is for the page that blocks access, and the other is for the page that stores the header part. And in this case, what I have is I need some additional space to effectively like align the other part of the allocation so that it can end on that boundary. What that means is I need to know how much extra it would take to pad the size that I wanted, right? In fact, now that I look at this too, since we're doing 2 times page size, this is not actually correct. This should have been this. Right? Because we don't need to account for the win32 memory block anymore when we're doing this stuff. Duh. Because we're making a whole extra page for that thing. Anyway, so what I was saying is now, OK, we do the underflow checking. It just works this way. We do the overflow checking. Now what we want to say is, well, we don't really know what this size is quite yet. We know we need the 2 extra pages. We also need this size to be rounded up to the next boundary of pages, right? So we need to sort of say, what is that rounded up version? And we also probably want to do a thing here where we're like, OK, base offset. And what we could do with the base offset is say, well, if you look at what happened, we'll start it out at 0. If you look at what happened in the case where we have the underflow checking, you can see that we did the base, we added 2 times the page size to it. So what we could do there is say, well, when we actually set that base pointer, right, like right here, we don't really have to do that here. We could do that up here. And so when we set the base pointer, we could say like, all right, wherever that base pointer is going to end up is now going to get offset. Well, I guess, yeah, no, that just works. So what we'll do is here in the base offset, we know that if we aren't doing any kind of overflow checking, it just has to move past the win32 memory block, right? So again, that would just be, here's the U8 of the block, and then we're going to add to it whatever that base offset is, right? So we're just going to move it past the header. However, in other circumstances, like in the one where we're doing the underflow checking, then we know that we want to move it up by 1 page size worth, right? This thing here, or 2 page size worth rather. 1 for the header page, and 1 for the page that's marked as "Don't touch this page," right? So in here we just have the base offset equals 2 times page size, right? So that's all there is to that. Now in the overflow checking case, we now know that there's going to be a base offset that's used to slide this up to align it. And so what we have to do is compute both what the total size is we need to allocate and what that offset is to put the actual base pointer at a location that will make it so the end of the allocated space lines up as close as possible to the memory end point, right? OK. And we do have one other thing that we have to do that has to do with alignment that hopefully I'll have time to do after this, but we'll get to that a little later. So anyway, what we need to do is say, if this size was going to be padded out to a full, like basically the entire 4K pages worth, whatever it would be, rounded up, right? So I basically need to round this up to a page size. Rounding it up to the page size is, rounded size, or size rounded up, just means that I have to essentially take whatever part of it was not. I don't know why my brain is explaining this poorly. Remember we had this guy, align pow2, right? Where we basically we add in 1 minus the entirety of the thing we wanted to do to sort of move it up to the next value, and then we get rid of anything in the bottom. It's essentially just saying, draw this out because my brain is for some reason too tired today to give a good verbal explanation of this, so I'm going to try and say it a little more clearly. So in integer space, right? We've got something that looks like like this. It's like 0, 1, 1, 0, 1 or something like this. And we know that what we want to do is we want to round up to the nearest thing on this side, right? And maybe there's even some stuff over here, right? So we want to round up so that we know that we're not using any of these bits, right? So what we do in order to do that is we just say, well, if we added this number, right? If we added all ones down here, then we know we would produce a 1 here, right, and carry forward if there was any bit set down here at all. And that's precisely the thing that we actually care about, right, is if there are any bits set down here. Because if you think about what happens, if I have a number and I say, like, I want to align it to a 16 byte boundary, right, then it doesn't matter whether I have 1, 2, 3, 4, 5, 6, any number other than 0, right, in that bottom part, in that bottom 0 to 15, which is what this would represent, right? Any number in that bottom part is too much. We will need to go up to another one. If it's all zeros, I wouldn't need to go up to another one. But if it's anything else, I do. So we want to add essentially one, just the number, whatever we're wrapping to minus 1, to do that bump. Then we clear out the bottom bits at that point because we know we've got the rounded up value. So this is all I'm trying to do. And so I'll do my align pow2. And I say the value that I wanted was the size, and the Win32 page size is the thing that I want to align it to. Now I know I have the size rounded up, so now I know that the size I'm using is size rounded up plus 2 times the page size. The base offset is going to be first the page size to get me past the header part, right? Then I'm going to add the size rounded up, which would get me to the end of the memory block, and then I want to go back however much I was actually trying to allocate so that I start and end right at that ending point, right? And then all the rest of the stuff should work the same. Now, once I do the underflow check or overflow check thing here, then what I need to do is the exact same thing that I would have done in the underflow checking case. But what I need to do now is say, instead of block plus page size, what I actually need to do is go up to, and you know what I could do actually now I think about it? If either of these are set, what I could do is just say protect offset, right? I could just do exactly the same trick and say, all right, there's going to be a protect offset. In the case where we're doing underflow checking, the protect offset is just the page size, right? In the case where we're doing overflow checking, it's going to be the page size plus the size rounded up. So it's going to be like all the way to that final page. And then it just runs this in either case. Since, I suppose since the protect offset itself is set to 0 when there isn't anything in particular that's being protected, I suppose we could also have done this by just saying if protect offset, but this is a little bit more correct at the moment, so I'm going to leave it that way. All right, so in theory that will do the overflow checking now, but I'm not entirely sure. And hey, it looks like it did, because remember we inserted this line as a bug yesterday to say when our overflow checking worked, it will catch this error, and it caught the error, right? Remember, that was just a silent bug we inserted that we never would have known was there until we saw some bad behavior when it overwrote something, and now we actually know that we can catch it. So that's pretty awesome right there. Let's go actually remove that because, hey, we don't want to leave the bug in that we inserted intentionally. But now we know at least that our overflow checking will catch overflows. OK, so where did we add that guy? All right, there. Go. And now we're good. So if I run it again, now we should be just overflow checking our actual code now. And like I said before, I think I had a question yesterday on the Q&A where someone said they were asking, why are we adding overflow checking if it hasn't come up yet? And I believe that my answer to that, hopefully is prescient here, assuming that we're actually doing it properly, is that we don't actually know that we don't have any, right? The whole point of overflow checking is not to catch overflow bugs that you are having currently necessarily. They're to find any overflows you might have that are not causing obvious problems yet, because typically the most difficult underflow or overflow bugs to catch are ones that don't immediately manifest themselves. The more immediately they manifest themselves, the less likely you are to need overflow or underflow checking to actually find them. So in this case, you can see we're getting an actual thing here. It suggests that we may just actually have a bug here. Now, we haven't really debugged our overflow checking itself yet, so it's a little bit premature to suggest that we know or don't know that something like that is happening. But let's take a look and see what is happening here. I'm not sure. This doesn't look particularly onerous. So it may be that we're, right, because this looks roughly correct to me. So I'm not sure why we're getting a one there. I wonder if we are slightly off on the way we're passing back. But you can see here, yeah, you can see here us getting the desk pointer out of this push. We are pushing one more than we need, which is what we would expect. We're then going through the characters for that, and we're putting them on there. It looks like at the end when we do desk length, which we should be able to do, right, that it's thinking that that's an overwrite on that. But I don't know why that would be an overwrite. Let's take a look, because now also one of the things we can do is we know that that desk pointer is actually like an individual allocation. Because when we're running in overflow checking mode, we know that each of them was allocated and will be basically on a page that we can then look at. So we should be able to take a look at it here and see. There it is. And we should be able to figure out whether it actually gave us the page boundary minus the amount that we requested, right? So length plus 1 in this case was 5. So we should know that we should be able to get 5 things. We should have been able to get 5 spaces before the end, right? It should have given us back 5 spaces before we would overwrite and have a problem. And let's see if we did. So we can see here we've got FFC, so we could trivially do the subtraction here and see how many we actually got, right? And that's definitely not the right number of characters to be able to write, because we should have been able to write to 5 locations, and in this case, we're only going to be able to write to 4 locations. Perhaps a more correct way to have written it so you could see that was this way. And so we have 1 that's missing there. And exactly as we would expect, because our bounds checking is protecting the page immediately after it, as soon as we try to write there, we're going to have a problem. So let's take a look. I don't know if the first time through this happens. It would be great if it did, and it does. So now we can at least debug what we're doing in our allocation that's making that not work properly. Let's take a look. So we compute our effective size for. The effective size for in this case is 5. So that's fine. That's what we would expect to see. And then we're going to say, what's the block size that we allocate? The block size is going to be 5. Again, totally fine. So let's go into our memory allocator here, where presumably we're having our problem. We can see our page size is 4K. The total size that we need to allocate is going to be 69 bytes, because the size is 5, and then the size of the Win32 memory block, of course, being 64 because it's cache line sized. We have the base offset is just going to be that, which we're not going to use because we're going to overwrite all these. Same with the protected offset. We don't have underflow checking on. We do have overflow checking on. So now we take a look at what our size rounded up is. Our size rounded up is 4096. That is correct, because if we're asking for 5, we know we'd only need 1 page, obviously, to store 5. So then we take a look at what our total size is. Our total size is going to be that 1 page, so it's going to be 3 pages, right? Which is what we would expect. So if I do total size divided by 4096, I should get 3 pages, and I do. So that's nice. Similarly, I can do it this way, just to make sure it's not a rounding thing. You can see it's exactly what we would expect. So then we take a look at what the offset's going to be. It's going to be 1 page forward, then it's going to be however much the size rounded up is minus that 5. Okay? And so what that should give us is it should give us, put it all the way past and then come back a little bit, right? All the way to the page boundary, but coming back a little bit. So that isn't really what we were seeing, and so we'll have to go take a look at why, but it could be that we're touching this somewhere a little bit further up, but let's double check. So if I come through here and look at what the base offset is, the base offset is 8187. So if we were to take a look at what we would expect that to be, 8187, you can see that it's putting it exactly where I wanted it. So that seems to be correct. And if I look at block base, you can see that that's not C, it's B, which is what we would expect. So where is that +1 coming from is what we need to know. We do the virtual protect. That's what we think we should do. So that's fine. We come back. We get our block. And now let me just see what we're doing here in terms of getting the actual memory. Get alignment offset may be our problem. Aha. Yes. So this is actually, I guess, the thing that I said when back a little bit beforehand, where I said we're going to have one more thing to do with alignment. Well, this was the thing. I wasn't sure if we'd ever hit it, but it looks like we will hit it because the default alignment of 4 is in effect even on things like strings, which can have odd alignments like that. So the problem that we have here is basically that we need to make sure that the size we pass down to the allocator is always aligned to the size we expect to align it to afterwards, because otherwise when it does the backup, it's not going to work, right? And so I'm not sure exactly the best way to do that. There's 2 ways we can do it. One way is we can modify the size first and then pass it down. And the reason that we would do that is because if we want to make sure that we are always clean in all the circumstances, we can do that. The only reason not to do that is if we do that padding, it means that if the next allocation was something that didn't actually need to be aligned itself, because it's an alignment of 1 or something else, then we shouldn't have done it because we're wasting a little bit of space. I'm not sure I care about that too much. But yeah, it's a little subtle, let's put it that way. So let's take a quick look here at what we would probably have to do to make that work OK. And I think that's the last thing as far as overflow or underflow checking is concerned. I don't think there's anything else in particular that we need to be aware of. So if I come through here, then essentially what's going to happen is once I do this allocation, I'm going to get back something that's been slid up to the end of the boundary. At that point, because we slid it up to be right before the boundary, if its size wasn't aligned to the size, to the alignment that we wanted, we're effectively doing that sliding up is going to unalign it. And then we're going to try to align it by applying the alignment offset, and that's going to make it be in the wrong place, right? That's going to ruin our fun. So again, we have 2 choices here. One is we can make sure that the size is always also aligned. That way, when we go down to the subsystem, the Win32 subsystem, it will leave us aligned because the size itself will have been aligned. The other thing we can do is pass the alignment down to the Win32 subsystem so that when it does the adjustment, it will back align, it will move it back the amount that it needs to for the alignment. Yeah. I think what I'm going to do is just say, let's go ahead and do let's go ahead and align it to the alignment that it's asking for. That just seems like maybe an easier thing to do. And so I'll just say, all right, initialize to the size in it. If we're going to be in one of these overflow or underflow checking scenarios, then what I want to do is say the size equals align pow2. And we'll pass in itself, and then whatever the alignment is that we're currently using. And now we shouldn't have that problem, right? In theory now, when we do this and we do the allocation, in theory now, the pointer that we got back, where is the pointer that we got back? There it is. Should be properly 4-byte aligned, and you can see that it is. It left 8 characters, right? And so as you can imagine, it's kind of annoying because now we get worse. We always will get worse bounds checking, but there's really nothing we can do about that, right? We can only get as good a bounds checking and still maintain alignment. We can't get any better bounds checking and still maintain alignment, right? If that makes sense. And alignment is like a hard requirement in a lot of cases. All right. So hey, sadly for us, it looks like, I mean, maybe good job for us. I don't know which one to say, but it looks like there aren't any particular overflow bugs to catch that we had in our code at the moment. So hey, I guess we did a good job on that before, but we do now know that we can check for them, right? And so that's all well and good. What we want to do now, too, is make sure we don't have to check for that, right? We can always turn off our bounds checking and then run, and we should be back to our nice zippy frame rate because now things are never calling the allocator, which is what we want. So that's it for the sort of debug allocation stuff. I don't think there's anything else in particular that we want to do. Let's make sure that we can still do loop code editing. Let's see here. That doesn't look good. Source block size. How is it getting set? Meowsers. That's just ridiculously big. Let's make sure, because like I said, we don't want to break anything. So let's see what happened there. We've got block size. What is? Where is my memory block? It's right here. So how did that size get set to an unusual value? What happened there? Let me take a closer look at it first before I try to figure that out. So we're looping through here, and I guess I would say this looks very suspicious. I'm not sure this is valid at all. In fact, it's definitely not, right? You can see this is kind of nonsense here. So let me take a look at what happened there. Let's jump in here. So there's our sentinel, and here's our blocks. I will say, not encouraging looking. That one looks reasonable. This one does not look even remotely reasonable. None of this looks at all reasonable. It's quite ridiculous. Quite. Whereas these all look very reasonable. So it looks like our next pointer is having some issues there. Let's take a look at why that might be happening. Oops. So here is our went through to memory block. When we are passing in this block, we're passing in that right there. We've got the next and previous pointers. We do the free memory block on this guy, which is what we would expect. So that all looks relatively good to me. We no longer need this page size in there. So that's good too. And presumably this can now move inside here also. So there we go. So what we want to do here is just figure out who is making our block act weirdly. You can see here where we're setting it. We always set the next pointer equal to the sentinel. We always set the prev pointer equal to the sentinel prev. I don't think any of these things, these are ticketed here. I don't know if anything else would have to be ticketed. It doesn't look like it would be. because that's the only thing that actually touches part of the linked list as far as I can tell. None of these other ones would really be involved, I don't think. So that all looks pretty reasonable. I'm going to take a look and see if I can spot, we'll leave it for tomorrow if I can't spot it, but I want to take a quick look just to see if there's an obvious reason why that's happening. Let me take a look at the first time a block is freed. Just want to see what the values are here. So here's the first time a block is freed. And you can see that I assume that this is the Sentinel here. In fact, you can tell it is because here's the hard address for it. So it's actually obviously not a dynamic allocation. So the next one here is the Sentinel. And you can see there's quite a few allocations already on the table before we actually free one of these allocations. But at the moment, anyway, if you look at the Sentinel, it's not wrong. Like it looks just fine. So we take the mutex, we set the next and prev pointers, and then it still appears to me like everything is relatively good, right? Like, I don't see anything particularly unusual here going on. So I'm not sure where that corruption is necessarily coming in, but let's go ahead and keep running here. There we go. And so for whatever reason, when we actually get in here now, you would think that we would have seen some error by now in the usage, but for some reason we don't. But then if we take a look now at the Sentinel, we will see, I think, that next pointer is messed up. Yeah. So I'm going to leave that one because that might take a while to track down. So let's go to the Q&A first, and then we'll track that one down, and then I think we're done. Loving that Q&A session repeater thing. It looks like HMDbot is doing it now. So it's not in InsoBot. Oh, no, I see. InsoBot replicates the QA, and then HMDbot prints out the actual information. Can we just talk about how InsoBot is like a national treasure, international treasure at this point, really? That is a great question InsoBot just asked. Bashing Tim Berners-Lee, inventor of the outer loop from zero to free everything. It's kind of like InsoBot is sort of like the beat poet of our generation. There was a great cartoon from a long time ago called Technological Threat. I don't know if you ever saw it, but it was basically like this like office that slowly got replaced with computers or whatever. And it reminds me of what's happening in the chat with all these bots taking over. Program script, maybe set the default alignment to 1 when in memory checking mode. Yeah, that does seem like a good idea. We would require a pound define for that. Let me put this in the to-do list. Maybe we'll do that. We did this. Set default alignment to 1 in Overflow Underflow Checking Nodes. Because that's not called on the arena. We could maybe make that work, though. We could maybe make that work. And also debug loop or mem block list corruption. There we go. I know this is a little off topic to what you're currently doing on stream, but what role does a software driver play, if any at all? To what are you referring when you say software driver? I guess I would say the reason that phraseology was a little confusing is because all drivers are software. So do you mean a driver like a software rasterizing, like a software OpenGL driver, as opposed like one that does the rendering in software instead of driving a graphics card? Or is there something, I'm not sure I understand the question. Continuing, no, you can make a C++ project that enables you to use resources that you can't use in user mode in the kernel. I understand, I think, what you're saying. So what you're talking about is installing something as a driver that exposes something to you that you would normally have to be in kernel mode to access. So that is definitely something. It depends largely on the operating system when you need that and when you don't. So for example, on Windows, file systems have to have a driver, right? In order to be a file system, you have to be a driver. So you can't just write an app that you run in user space that implements a file system. So one of the things that people have done is made a driver that all it does is forward all of the driver calls out into user space so that you can implement user mode file systems, right? I guess what I would say is I don't have much to say on that topic. That is generally just something that has to do with what your operating system considers privileged and what it doesn't. And certainly anytime you want to access something that is relatively hardware related, such as implementing a file system or accessing performance counters of some kind that may be protected, depending on how your operating system works, you may have to implement a driver in order to get at that stuff, because by default, the operating system is not going to run your application in a way that it can get it. Sometimes that's because of protections. So sometimes that's like, I want to access something on the hardware that the operating system prevents me from doing so if I'm not a driver. Other times it may just be because that's the way the operating system's API is set up. So for example, with the file system stuff, it's not so much that the operating system is trying to prevent a user space application from accessing something like a Sdg drive. It's because the fundamental infrastructure for how hardware like an Sdg drive or something is implemented in Windows is that it all stays in kernel space, presumably for performance reasons, right? So you just have to be down at that level if you want to interact with the operating system that way. But there's nothing inherently stopping you from just forwarding those calls out to a user space thing and then processing them there. It's just that the operating system doesn't do that by default because it wants to be more efficient or something, right? So that's usually how those sorts of things go. But you're doing it usually for one of those two reasons. Either you're trying to forward operating system API stuff out to the user level, and that API stuff really only exists at the kernel level, or you're trying to access something that's protected so that the user, it's not something that the operating system set up an API for necessarily, but it is something that the application can't get at because it's walled off. And the only place the operating system allows you to get at it is if you're in kernel mode. What are we doing here, people? There's no more Q colons. If there's no more Q colons, I'm done. I guess I'm done. All right. Thank you, everyone, for joining me for another episode of Handmade Hero. It's been a pleasure coding with you, as always. If you would like to, follow along at home with the series, you can always pre-order the game on handmadehero.org, and it comes with the source code so you can experiment yourself. We also have a forum site you can go to if you want to ask questions, a Patreon page if you want to support the video series, a schedule bot that tweets the schedule at you if you would like to know when we're going to be live, and an episode guide that you can use to catch up on past episodes. That is it for today and for the week. Tomorrow is no stream. I will be back next week, so do check the Tweetbot for more information on that. Until then, have fun programming, everyone, and I'll see you guys on the internet. Take it easy, everybody.